What if the universe isn't just something we observe, but something we create? This isn't science fiction. It's a question that's been haunting physicists and philosophers for decades, and it all hinges on one strange, almost magical idea: the quantum observer effect. Picture this: a particle doesn't have a definite state until you look at it. It's not just that we don't know what it's doing until we measure it. It's that our act of looking somehow forces it to choose a state. Sounds impossible, right? Yet experiments keep confirming this bizarre behavior, as if reality itself is waiting for us to make up our minds. Now take that idea and stretch it further. What if this isn't just about tiny particles in a lab? What if it's about everything? The chair you're sitting on, the screen in front of you, even the stars billions of light years away. Could they all be waiting, in some sense, for consciousness to pin them down? It's a thought that blurs the line between science and philosophy, between observer and creator. And if it's true, it means you aren't just a passive spectator in the cosmos. You might be one of the architects shaping reality simply by being here to witness it. This is the rabbit hole we're diving into today. We'll explore how cutting-edge physics is colliding with age-old questions about the nature of existence, how the act of observation might be woven into the fabric of the universe itself. From the double-slit experiment to the latest theories in quantum mechanics, we'll unpack the evidence and the mind-bending implications. Because if consciousness really does play a role in shaping reality, then everything we think we know about the world might need a second look. Ready to question the nature of existence? Let's begin. The double-slit experiment is where things get truly strange, where quantum mechanics stops being a neat mathematical theory and starts behaving like something out of a cosmic magic show. Here's how it works. Imagine firing tiny particles like electrons one by one at a barrier with two narrow slits. If no one's watching, these particles don't act like solid little balls. Instead, they behave like waves, passing through both slits at once and creating an interference pattern on the other side, like ripples overlapping in a pond. But here's the twist. If you set up a detector to observe which slit each electron goes through, that interference pattern vanishes. Suddenly, the electrons act like ordinary particles going through just one slit. It's as if they know they're being watched and change their behavior to match. This isn't some glitch in the equipment. It's been replicated countless times with everything from photons to molecules. The shock wasn't just that particles could act like waves. It was that the mere act of observation seemed to force them to pick a side, collapsing all their possible states into one definite reality. Think of it like flipping a coin that stays spinning in the air until you catch it. Only then does it decide to be heads or tails. Except here, the coin is the entire universe's rulebook. What makes this even wilder is that it's not about human eyes or conscious intent. The observer can be a machine, a camera, anything that records or measures. The key is information becoming part of the system, so it's not about mystical consciousness bending reality. It's about the universe's rules being fundamentally shaped by interactions, by the flow of information. That's why this experiment rocked physics to its core. It suggests that reality isn't this fixed, objective backdrop. It's more like a conversation, a dance between what's possible and what's observed. And if that's true for electrons, why not for everything else? Could the universe be a vast quantum system, constantly in flux until some interaction pins it down? That's the unsettling beauty of this experiment. It doesn't just challenge what we see, it challenges what seeing even means. Every time we look, we're not just discovering reality. We might just be completing it. But what if the act of observation isn't just recording reality, but actively creating it? That's the bold claim at the heart of the von Neumann-Wigner interpretation, one of the most provocative ideas in quantum physics. While most interpretations treat wave function collapse as a random or mechanical process, this theory flips the script entirely. It suggests that consciousness itself, the subjective experience of an observer, is what forces quantum possibilities to snap into a single, concrete reality. Picture a universe where particles exist in a blur of potential until a mind, any mind, interacts with them. Suddenly, the math stops being abstract. The equations need someone to solve them. This wasn't just fringe speculation. Nobel Prize-winning physicist Neumann-Wigner became one of its most vocal defenders, arguing that observation isn't a passive glance but an active, creative force. He even proposed a now-famous thought experiment. Imagine a sealed lab where a scientist measures a quantum system. To an outsider, the entire lab, scientist included, should exist in superposition, a haze of unresolved states. But we never see that. Why? Wigner claimed it's because the outsider's consciousness collapses not just the particle state, but the entire lab's reality. In other words, the universe seems solid because minds keep stitching it together. Critics dismiss this as philosophy masquerading as physics, but the math doesn't rule it out. In fact, modern experiments keep nudging us toward uncomfortable questions. Take quantum delayed choice experiments, where decisions made after a particle's journey seem to rewrite its past behavior. Or the growing suspicion that even time itself might emerge from quantum interactions. The more we look, the more the universe seems like a participatory phenomenon, a cosmic canvas waiting for conscious brushstrokes. Of course, this raises dizzying implications. If consciousness shapes reality, whose counts are humans, are cats, are single-celled organisms, the line between observer and observed starts to blur, and suddenly, the universe feels less like a machine and more like a collaborative art project. Wigner himself admitted the idea borders on the mystical, but he insisted physics shouldn't shy away from hard truths, no matter how strange. After all, if the quantum world has taught us anything, it's that reality rarely plays by the rules we expect. Maybe it's time we considered that the ultimate rule maker, the real architect of the universe, has been staring back at us from the mirror all along. Schrödinger's cat might be the most famous feline in physics, not because it's alive or dead, but because it's both at once. At least, that's how the thought experiment goes. Seal a cat in a box with a vial of poison set to release if a radioactive atom decays. According to quantum rules, until someone opens the box, the atom exists in a superposition. Decayed and not decayed, so the cat must be both alive and dead simultaneously. It's a paradox meant to expose the absurdity of applying quantum weirdness to everyday objects. But what if the joke's on us? What if the cat's ambiguous fate isn't just a quirk of the math, but a clue about how reality actually works? Here's where conscious observation enters the picture. If the universe truly waits for an observer to collapse quantum possibilities into a single outcome, then the cat's fate isn't just unknown, it's undecided. The box isn't hiding the truth, it's holding reality in suspense. No decay, no poison, no living or dead cat. Just a fragile web of probabilities, teetering until a conscious mind peers inside and forces the universe to choose. It's a staggering idea, life and death hanging in the balance, not of physics but of perception. Critics argue this interpretation stretches quantum mechanics beyond reason. After all, cats and vials and Geiger counters are made of particles that should obey quantum rules independently of human observation. But supporters counter with a provocative question: why should size or complexity matter? If a single electron state depends on interaction, why wouldn't an entire system? The real shock isn't that a cat could be in superposition, it's that we're so sure it can't be. Our intuition insists reality exists out there, solid and separate from us, but quantum mechanics keeps hinting that intuition might be wrong. Modern twists on Schrödinger's experiment only deepen the mystery. Scientists have now created quantum cats in lab superpositions of tiny objects visible to the naked eye, like vibrating strips of metal or clouds of atoms. These aren't metaphorical cats, they're tangible things existing in multiple states at once until measured. The line between quantum and classical, between the tiny and the tangible, keeps blurring. And if a strip of metal can straddle two realities, why not a cat? Why not a planet? Why not us? This isn't just about feline mortality. It's about the unsettling possibility that reality, at its core, is fluid, a tapestry of maybes waiting for observation to weave them into certainties. The cat isn't the puzzle. We are. Every time we open the box, we're not just discovering what's inside. We might be deciding it. Quantum entanglement is where the universe stops pretending to play by ordinary rules. Imagine two particles born from the same quantum event, forever linked no matter how far apart they drift across a room, a planet, or even galaxies. Change one, and the other instantly responds as if space and time don't exist for them. Einstein called this spooky action at a distance, convinced it revealed a flaw in quantum theory. But decades of experiments, from photon pairs to diamonds separated by miles, keep proving him wrong. The particles do coordinate faster than light could travel between them, smashing our classical intuition about how reality should work. Here's where it gets even stranger. These entangled particles don't just defy distance, they seem to defy time itself. In delayed choice experiments, scientists can tweak the settings of a detector after the particles have already begun their journey, and yet the particles adjust their behavior retroactively, as if the future decision reached back to rewrite their past. It's as though the universe refuses to settle on a definitive version of events until consciousness, in the form of measurement, forces its hand. This isn't just about particles communicating in secret. It's about the fabric of reality remaining unresolved until an observer steps in. Think of entanglement like a cosmic game of choose-your-own-adventure, where every possible storyline exists in parallel until someone reads the page. The particles aren't secretly whispering to each other, they're waiting, suspended in a haze of potential until the moment they're observed. Then, and only then, does their shared story snap into focus. What's startling is how this challenges our deepest assumptions about objectivity. If entangled particles can't even have definite states until measured, then how much of the universe is just waiting? The stars, the planets, the chair beneath you, could they all be holding their breath, entangled in some vast quantum web until consciousness interacts with them? It's a humbling thought. Reality might not be a pre-recorded film, but a live performance, unfolding only as we watch. Critics argue there must be hidden variables, unseen mechanisms forcing particles to sync up. But Bell's theorem, a mathematical proof tested repeatedly, shuts that door. The universe genuinely operates this way, with no hidden strings pulling the particles. The only mechanism appears to be the act of observation itself. And if that's true, then entanglement isn't just a quirk of tiny particles. It's a hint that the universe is fundamentally participatory, a dance where every step depends on who's watching. So where does that leave us? Not as passive witnesses to a finished cosmos, but as active participants in a reality that's still being woven, one observation at a time. The spookiness isn't in the particles, it's in realizing that the universe might need us just as much as we need it. John Wheeler didn't just ask whether observers create reality, he designed experiments to test it. This was the heart of his participatory anthropic principle, the idea that the universe only becomes real because conscious beings are here to perceive it. Wheeler saw the cosmos not as a static stage, but as an unfolding story, one that requires an audience to give it meaning. His most famous thought experiment, the delayed choice experiment, takes quantum weirdness and stretches it across time itself. Imagine a photon traveling from a distant quasar, its path bending around a galaxy billions of years ago due to gravity. According to Wheeler, we can wait until today, long after that photon's journey began, to decide whether it behaved like a particle or a wave. Set up a detector to measure its path, and it retroactively chooses to act like a particle. Remove the detector, and it remembers it was a wave all along. The implications are staggering. Present-day observation reaching back to sculpt events from the dawn of time. Wheeler's vision went far beyond photons. He proposed that the universe is built like a vast feedback loop where observation doesn't just record history, it authors it. In his words, we live in a participatory universe where the mere act of asking questions shapes the answers reality provides. Think of it like a cosmic version of the old philosophical question. If a tree falls in a forest with no one to hear it, does it make a sound? Wheeler's answer was radical. Without an observer, there might not even be a tree. Or a forest or time. The universe, he argued, only crystallizes into existence when consciousness engages with it. Skeptics dismissed this as poetic speculation, but modern physics keeps finding echoes of Wheeler's ideas. Quantum retrocausality experiments now show particles responding to measurements that haven't happened yet, as if the future whispers backward to guide the past. Cosmologists debate whether the fine-tuning of physical constants, the precise balance that allows life to exist, could imply the universe needed observers to stabilize its laws. Even the search for extraterrestrial intelligence takes on new urgency under Wheeler's principle. If consciousness truly weaves reality, then finding other observers might reveal how deeply the cosmos is stitched together by perception. The most haunting question isn't whether Wheeler was right. It's what his theory says about us. If reality remains half-formed without observers, then human minds aren't accidents in an indifferent universe. We might be co-conspirators in creation, our curiosity the chisel that carves the quantum fog into stars, planets, and history. Every time we look up at the night sky, we're not just stargazers. We might be the universe's way of finally seeing itself. What if the universe isn't just shaped by observation, but literally built like a cosmic computer program? This is where the quantum observer effect collides with one of the most provocative ideas in modern physics, the simulation hypothesis. The theory suggests our reality might not be fundamental, but instead a meticulously rendered digital construct. And strangely, the same quantum behaviors that hint at observer-created reality also point to eerie parallels with how virtual worlds operate. Think about how video games work. A game engine doesn't render every leaf on every tree in a forest at once. It only loads details when a player looks at them. Unobserved areas remain in a fog of potential saving processing power. Now compare that to Schrödinger's cat or the double-slit experiment, where reality seems to stay in an unresolved state until observed. The similarities are unsettling. Could the universe be running on similar optimization rules, collapsing probabilities into concrete events only when conscious observers interact with them? Digital physics takes this further by proposing that spacetime itself might be pixelated, not smooth and continuous, but made of tiny, indivisible chunks like the pixels on a screen. Planck length, the smallest possible unit of space, and Planck time, the tiniest measurable moment, could be the universe's resolution limits. Even more striking, quantum entanglements, instantaneous connections across vast distances mirror how data in a simulation might reference itself globally, bypassing the speed of light, just like variables in a program can update everywhere at once. Some scientists argue this isn't just analogy. The mathematical precision of physical laws, the way information seems to be the fundamental currency of reality, as in black hole thermodynamics, and the apparent fine-tuning of constants for life all hint at something designed rather than emergent. Nobel laureate Frank Wilczek even coined the term quantum information to describe how the universe might fundamentally process data. But here's the twist: if we are in a simulation, who's the programmer? Simulation theory usually imagines advanced aliens or future humans running the code, but digital physics opens another possibility. What if consciousness itself is the substrate, not a byproduct of the simulation, but the very thing generating it? This loops us back to Wigner and Wheeler's ideas. Observers don't just perceive reality, they complete its rendering. the universe might not be a simulation running on silicon. It could be a shared mental construct, a cosmic game where consciousness is both player and engine. Critics dismiss this as untestable metaphysics, but experiments are probing the edges. Physicists have proposed looking for glitches, energy anomalies, rounding errors in cosmic constants, or unexpected limits in high-energy particle collisions that might reveal the universe's source code. Others suggest quantum gravity experiments could uncover whether space-time truly behaves like a lattice at microscopic scales. Whether or not we're living in a simulation, the deeper question remains: why do quantum mechanics and digital physics align so neatly with the idea that reality is interactive, observer-dependent, and potentially computational? Maybe the answer isn't about the nature of the universe, but the nature of us. After all, every simulation needs an interface, and if consciousness is that interface, then the most profound discovery awaiting us might not be outside in the cosmos, but locked within the act of perception itself. The human brain might be more than just a sophisticated biological computer. It could be a quantum instrument, fine-tuned to interact with the fabric of reality itself. This is the bold claim at the heart of neuroquantology, a field that bridges neuroscience and quantum physics to explore whether our minds play an active role in shaping the universe. At the center of this idea is orchestrated objective reduction, or ORCH, a theory developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness isn't just a byproduct of neurons firing, it's a quantum process happening deep within the brain's microtubules, tiny protein structures inside cells. These microtubules, they argue, could be where wave functions collapse, transforming quantum possibilities into the concrete experiences we call reality. Imagine your brain as a quantum orchestra with microtubules acting as the conductors. Every thought, every sensation might involve a symphony of quantum states resolving into coherence, like notes crystallizing into a melody. Penrose and Hameroff suggest this isn't just metaphor, it's physics. When quantum superpositions in microtubules reach a threshold of complexity, they collapse in a way that generates conscious moments. This collapse isn't random, but orchestrated by the brain's structure, creating the seamless flow of awareness we take for granted. It's a radical departure from classical neuroscience, which treats the brain as a purely biochemical machine. Instead, ORCH implies the mind doesn't just perceive reality, it helps construct it. Critics, of course, have raised eyebrows. Quantum effects are notoriously fragile, easily disrupted by the warm, noisy environment of the brain. How could delicate superpositions survive in such chaos? Supporters counter with examples like photosynthesis, where quantum coherence plays a role in energy transfer even in biological systems. And recent experiments hint at quantum vibrations in microtubules, though the debate remains fierce. What's compelling, though, isn't just the science, it's the philosophical shift. If ORCH is even partially correct, it blurs the line between observer and observed in a way that echoes the deepest mysteries of quantum mechanics. Other theories push the boundary further. The thalamocortical model suggests the brain's thalamus acts as a quantum interface, filtering and collapsing probabilistic inputs into a unified conscious experience. Meanwhile, some researchers propose that neural networks exploit quantum entanglement to process information in ways classical physics can't explain. These ideas remain speculative, but they share a common thread. The brain isn't just a passive receiver of reality. It might be an active participant, engaging with the quantum underpinnings of existence in ways we're only beginning to glimpse. The implications ripple far beyond lab experiments. If consciousness arises from quantum processes, it could explain phenomena like intuition, creativity, or even the elusive flow state, where time seems to dissolve and decisions arise effortlessly. It might also shed light on near-death experiences or altered states of consciousness, where the brain's quantum systems could temporarily decouple from classical constraints. And if the mind truly interacts with quantum fields, it raises a haunting question. Are we, in some small way, shaping the universe just by being aware of it? Skeptics demand harder evidence, and rightly so, but the mere possibility rewrites the relationship between mind and matter. For centuries, science has treated consciousness as a ghost in the machine, an ephemeral shadow cast by physical processes. Neuroquantology turns that view on its head, suggesting the ghost might be the mechanic tuning the machine's very workings. Whether or rival theories prevail, one thing is clear: the brain's connection to quantum physics isn't just a fringe idea anymore. It's a frontier, one that could redefine what it means to be both observer and creator in a participatory universe. Long before quantum physics puzzled scientists in labs, Eastern mystics were grappling with a strikingly similar idea that reality might not be as solid as it seems. In Hindu philosophy, the concept of Maya describes the universe as a grand illusion, a veil that tricks us into perceiving separation and permanence where there's only flux and interdependence. The Upanishads, ancient texts dating back over 2,000 years, speak of a world where the observer and the observed aren't truly distinct, where consciousness isn't just a witness but the very ground of existence. Sound familiar? It's as if these sages glimpsed the quantum observer effect millennia before microscopes or particle colliders. Buddhism takes this further with the principle of dependent origination, which holds that nothing exists independently. Every phenomenon arises only in relation to everything else. A tree isn't just a tree, it's sunlight, soil, rain, and the act of perceiving it, all woven together in a web of mutual creation. Remove one thread and the whole tapestry unravels. This mirrors the quantum view, where particles have no definite properties until they're measured, where reality emerges from relationships rather than solitary building blocks. The Buddha's ancient insight, all phenomena arise in dependence upon conditions, could almost be a poetic summary of quantum entanglement. What's uncanny isn't just the similarity of ideas, but the methods behind them. Eastern mystics didn't use telescopes or equations. They turned inward, honing perception through meditation to peel back layers of assumed reality. In deep states of samadhi, practitioners reported experiencing the dissolution of boundaries between self and world, a oneness that aligns eerily with quantum non-locality, where separated particles remain inexplicably linked. The mystic's revelation, Atman is Brahman, the self is the universe, resonates with Wheeler's participatory universe, where observer and cosmos co-create each other. But here's where the parallels get provocative. Advaita Vedanta, a school of Hindu philosophy, asserts that consciousness is the only true reality. Everything else is projection, like images on a movie screen. Modern physics doesn't go that far, yet the quantum measurement problem leaves a similar door ajar. If observation collapses wave functions, is consciousness somehow fundamental? The Tibetan Buddhist concept of empty luminosity describes reality as both void of inherent existence and radiant with potential, a description that could double as a poetic take on the quantum vacuum, teeming with virtual particles waiting to manifest. Critics argue these connections are superficial, that ancient wisdom was metaphorical while physics is literal. Yet the overlap is hard to dismiss. When the Dalai Lama says, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it," he's pointing to the same awe that mystics cultivated centuries ago. Both traditions, in their own ways, confront the unsettling truth that reality isn't a fixed backdrop. It's a dynamic interplay, a dance where the dancer and the dance can't be pulled apart. Perhaps the most humbling lesson lies in what these perspectives share: a universe far stranger, far more interactive than our everyday senses suggest. Whether through meditation or mathematics, the message echoes: what we call real might just be the beginning of the story. Not everyone buys the idea that consciousness shapes reality. In fact, most mainstream physicists roll their eyes at the suggestion. To them, the universe doesn't need observers to exist, it just does. Their counterargument hinges on a process called decoherence, and it's the closest thing quantum mechanics has to a demolition crew for the observer effect. Here's how it works when a quantum system interacts with its environment, whether air molecules, stray photons, or even the vibration of atoms in a detector. It doesn't stay in a delicate superposition for long. Those interactions leak quantum information into the surroundings, effectively erasing the system's wave-like behavior. The result, what looks like wave function collapse, but without any need for conscious observation. This isn't just theory. Lab experiments show decoherence in action. A particle might start in superposition, but the moment it brushes up against the messy real world, its quantum magic fades. Critics argue this explains why we don't see cats or chairs in two states at once. They're constantly bombarded by their environment, forcing them to pick a classical state long before a human ever looks. Nobel laureate Serge Haroch demonstrated this by tracking how quickly photons lose coherence when exposed to even tiny disturbances. The takeaway: reality might not need us to settle its ambiguities. The universe could be enforcing its own rules, no observers required. Skeptics go further, pointing out that if consciousness caused collapse, we'd need to define what counts as an observer. Does a bacteria qualify? A thermostat? The ambiguity opens a Pandora's box of paradoxes. Physicist Sean Carroll puts it bluntly: the moon exists whether you look at it or not. He and others favor the many worlds interpretation, where wave functions never collapse at all. Instead, every quantum possibility plays out in branching parallel universes. In this view, observation isn't creative, it's just you becoming aware of one thread in an infinite tapestry of realities. No mystical consciousness, just cold, endless math. Yet the debate isn't one-sided. Even decoherence has gaps. It explains how superpositions disappear, but not why we experience one outcome over others. The measurement problem lingers like a stubborn ghost, and while many worlds sidesteps the observer issue, it replaces it with an unfathomable multiverse. Some physicists, like David Deutsch, embrace this, arguing that Occam's razor favors many worlds over mysterious collapses. Others, like Roger Penrose, retort that consciousness might exploit gaps in decoherence, perhaps in the brain's microtubules where quantum effects could persist. What's fascinating isn't who's right, but how raw the disagreement remains. The same equations that predict quantum behavior with uncanny precision still can't tell us what's really happening. Decoherence offers elegance, but at the cost of reducing consciousness to a spectator. The observer effect, meanwhile, grants the mind a starring role but risks veering into metaphysics. The irony: both sides agree on the data. They just tell wildly different stories about it, and that's the heart of quantum mechanics, not a puzzle to solve, but a mirror reflecting how deeply our assumptions shape what we call reality. The multiverse interpretation doesn't just sidestep the question of observer-created reality, it blows the door off its hinges. In this radical view, every quantum decision spawns not just one outcome, but every possible outcome, each playing out in its own parallel universe. Forget about collapse, forget about observers forcing reality to choose. Here, the universe refuses to pick sides. When an electron faces a choice, go left or right, spin up or down, it doesn't settle. Instead, the cosmos splits, creating two new branches, one where the electron went left, another where it went right. The same goes for every quantum event, from photon paths to human decisions, meaning there's a universe where you took that job offer, one where you didn't, and countless others where every atom in your body made slightly different choices. What makes this idea so compelling is its ruthless simplicity. Unlike interpretations that rely on mysterious collapses or conscious observers, the many worlds theory treats quantum mechanics like a vast, unbroken equation. Schrödinger's wave function never collapses, it just keeps evolving, weaving an ever-expanding tapestry of realities. No special rules for measurement. No need to explain why observation magically changes things. It's a democratic universe where every possibility gets its own stage, no audience required. But elegance comes at a cost. If every quantum possibility manifests somewhere, then the multiverse is unimaginably vast, not just billions of worlds, but an infinite fractal of them. Critics argue this violates Occam's razor, the principle that simpler explanations are preferable. Why posit an infinity of unseen universes just to avoid wave function collapse? Supporters counter that the math already describes branching. It's collapse that adds unnecessary baggage. As physicist David Deutsch puts it, the multiverse is already there in the equations. Denying it is like insisting the Earth is flat because you can't see the curve. The real tension, though, isn't just about elegance, it's about what we value in a scientific theory. Observer-driven interpretations like Wigner's or Wheeler's give consciousness a starring role, aligning with deep philosophical questions about perception and existence. The multiverse, by contrast, feels coldly mechanistic, a cosmic assembly line churning out realities with no need for minds to shape them. Some find this liberating. Reality doesn't depend on us. Others find it alienating, stripping the universe of meaning by making everything that could happen equally real. There's also the thorny issue of testability. If every possible outcome occurs somewhere, how do we verify the theory? Multiverse advocates point to subtle quantum effects or cosmic inflation patterns as indirect evidence, but critics demand more. Without a way to observe or even infer other branches, the theory risks drifting into metaphysics. Meanwhile, interpretations favoring observer effects at least tie reality to measurable interactions, even if consciousness remains a puzzle. Yet for all its extravagance, the multiverse solves one problem beautifully: the randomness of quantum outcomes. In a single universe view, it's baffling why measurements yield one result over another. But if all results happen, there's no randomness, just branches. It's a trade-off: accept infinite worlds, and the universe never has to choose the price. Admitting we're just one thread in an unimaginably vast fabric, where every crossroads leads not to one destiny, but to all of them. Whether you find this reassuring or unsettling, the multiverse forces us to confront a humbling truth: our intuition about reality might be hopelessly narrow. The cosmos could be far stranger, far grander than our classical senses suggest. And if the many worlds interpretation is correct, somewhere out there, another version of you is nodding along while another shakes their head, and another wonders if any of this is real at all. Time seems to march forward, an arrow flying in one direction past to present to future. But quantum mechanics laughs at our linear assumptions. In the quantum realm, events might not just influence the future. They could reach back and reshape the past. This isn't science fiction. It's the startling implication of quantum retrocausality, where the act of observation doesn't just reveal reality, it rewrites history. Take the delayed choice quantum eraser experiment, a mind-bending twist on the classic double-slit setup. Here, particles are fired at a barrier, but scientists wait until after they've passed through the slits or spread out as waves to decide whether to measure their path or erase that information. Astonishingly, the particles seem to know this future decision, adjusting their past behavior accordingly. If the experimenter chooses to measure, the particles retrospectively act like discrete objects. If they choose to erase the measurement, the particles remember they were waves all along. It's as if time itself hesitates, refusing to settle on a version of events until the observer makes their choice. This gets even wilder with quantum entanglement. Imagine two entangled particles separated by light years. Measure one, and its partner instantly assumes a corresponding state, no matter the distance. But what if the measurement on the second particle happens before the first? From one perspective, it looks like the future measurement reaches backward to influence the past. Nobel laureate Yakir Aharonov proposed that particles might carry advanced waves from the future, interacting with retarded waves from the past to create the present moment. In this view, time isn't a one-way street. It's a loop where cause and effect blur into a mutual dance. Critics argue this is just a quirk of interpretation, that retrocausality is a mathematical illusion, not real physics. But supporters point to concrete tests. In 2018, scientists at the National University of Singapore performed a quantum-delayed choice experiment where the decision to measure or not was made by a random number generator after the particles had already passed through the apparatus. Yet the particles still behaved as if anticipating the future choice. The results fit retrocausal models eerily well, suggesting the universe's script isn't written in stone. It's more like a draft constantly revised by observers. What does this mean for time's arrow? Thermodynamics insists entropy always increases, giving time its direction. But quantum retrocausality hints that at the smallest scales, time might be bidirectional, a river that flows both ways. Some theorists, like physicist Hugh Price, argue that our perception of time as linear could be an emergent property, a statistical illusion created by countless quantum events averaging out. Just as a flipped coin looks random but follows deterministic physics, time's arrow might emerge from deeper, timeless quantum rules. If true, this reshapes not just physics but philosophy. Free will, destiny, even the nature of memory, all get tangled in retrocausality's web. Are our choices truly ours if the future can tug on the past, or is the universe playing a cosmic game of 20 questions where every answer adjusts the question that came before? One thing's certain, in a quantum world, time doesn't just tick forward. It spirals, loops, and folds, waiting for observers to trace their fingers along its seams. What happens when observation isn't just an individual act but a collective one? If a single mind can influence quantum states, could millions of minds together shape the fabric of reality itself? This is the tantalizing premise behind collective consciousness effects, the idea that shared human attention might weave the consensus world we all experience. Take the legendary Maharishi effect, named after the yogi who first proposed it. Studies suggest that when large groups meditate together focusing on peace, crime rates in nearby areas temporarily drop. Skeptics dismiss it as coincidence, but meta-analyses across dozens of cities show patterns hard to explain by chance alone. It's as if concentrated awareness acts like a tuning fork, resonating through the quantum field to nudge probabilities toward harmony. Then there's the Global Consciousness Project, a decades-long experiment run by Princeton researchers. They deployed random number generators worldwide, machines that spit out zeros and ones in no predictable order. The hypothesis: if mass consciousness truly interacts with reality, these machines should deviate from randomness during events that unite global attention. Think royal weddings, terrorist attacks, or World Cup finals. Astonishingly, that's exactly what the data reveals. During moments of collective emotion, the machine's output becomes slightly less random, as if the weight of millions of minds briefly warps the statistical fabric of reality. Critics argue these findings are cherry-picked or statistical flukes, yet the implications are too provocative to ignore. Quantum physics already shows particles entangling across distances. Could human minds share a similar, subtler connection? Some theorists propose that our brains might function as biological quantum antennas, tuning into a shared field of potential. When enough minds focus on the same idea or emotion, they could collapse quantum possibilities into a stable consensus, like a crowd chanting in unison, suddenly hearing their voices amplify. This might explain cultural shifts, how fashion trends explode, or why societal norms transform almost overnight. The most radical version of this idea comes from systems like manifesting or the law of attraction, where collective belief allegedly molds reality. While these often drift into pseudoscience, they touch on a deeper question. Is reality more like a Wikipedia page editable by anyone with enough consensus? If so, it raises haunting possibilities. Could prejudice or misinformation literally reshape social conditions by altering what enough people observe as true? Or could collective practices like mindfulness meditation heal societal fractures by recalibrating the shared field? Perhaps the answer lies somewhere between mysticism and physics. Just as quantum systems exist in superposition until measured, human experience might hover in a realm of potential until observation, individual or collective, pins it down. The world we agree on isn't necessarily the only one possible. It's just the one we've all chosen to see. And if that's true, then changing reality might start not with force or logic, but with a simple shift in what enough of us decide to notice. The line between science and the unexplained blurs when we examine psi phenomena, those elusive effects where human intention seems to reach beyond the limits of space and time. Take the work of researcher Helmut Schmidt in the 1970s. He designed experiments where participants tried to influence radioactive decay, a process so random even quantum physics can't predict individual events. The startling result, when people focused their intention on speeding up or slowing down the decay, the data shifted slightly but statistically significantly, as if consciousness was nudging the dice of reality. Skeptics chalked it up to flawed equipment, but subsequent replications with tighter controls kept finding the same anomaly. It's as if the observer effect isn't confined to labs with pristine quantum systems. It leaks into the messy macroscopic world too. Then there's the Princeton Engineering Anomalies Research Lab, where for nearly 3 decades, scientists documented thousands of trials where volunteers attempted to bias random number generators with their minds. The cumulative data revealed deviations from chance so consistent that statisticians calculated the odds of it being coincidence at less than 1 in a trillion. One particularly striking experiment involved remote viewers people asked to describe or influence distant locations. In some trials, their focused attention appeared to correlate with tiny but measurable changes in the output of sensitive detectors at those sites. Critics argue these effects are vanishingly small, but supporters counter that even a microscopic crack in the edifice of classical physics could hint at a deeper truth, that consciousness and matter aren't as separate as we assume. Biological systems add another layer of intrigue. Studies in the field of direct mental interaction with living systems, or DMILs, suggest focused intention might affect everything from the growth rate of bacteria to the healing of wounds. In one often cited experiment, researcher William Broad had participants attempt to mentally calm or agitate live animals, like gerbils in separate rooms, merely by concentrating. The animals' physiological responses, measured by heart rate and movement, showed correlations with the human intent despite no physical interaction. Similar experiments with human, healers, and cell cultures found that directed intention sometimes altered cell proliferation rates, even when the healer was miles away. The effects were inconsistent. Some trials worked, others didn't, but the sheer volume of positive results across labs raises eyebrows. Why does this matter? Because if even a fraction of these findings hold up, they challenge the bedrock assumption that mind and world are separate. Quantum mechanics already hints that observation isn't passive, but psi phenomena suggest intention might be a force, however subtle, that resonates through the fabric of reality. The common thread, information. Whether it's a random number generator or a living cell, the systems that respond to intention all share one trait. They're complex, dynamic, and sensitive to tiny fluctuations. Like a whisper that shifts a snowpack into an avalanche, consciousness might exploit these pivot points, bending probabilities in ways we're only beginning to map. Of course, the scientific establishment remains deeply divided. For every study showing anomalous effects, there's another failing to replicate it. The controversy isn't just about data, it's about worldview. Accepting that consciousness influences matter outside the brain forces a reckoning with materialism. The the doctrine that everything is reducible to physical interactions. Yet dismissing these phenomena outright risks committing the very sin science warns against, ignoring evidence because it contradicts dogma. Perhaps the truth lies in between. Maybe consciousness doesn't control reality so much as dance with it, entangled in ways our current physics can't yet formalize. What's undeniable is the pattern that emerges across disciplines, from quantum physics to psi research to ancient spiritual traditions. Reality seems to respond to attention, not just record it. Whether that's a profound truth or a statistical mirage remains an open question, but the mere possibility reframes our role in the cosmos. We might not be gods shaping worlds with our thoughts, but we're likely more than mere spectators too. The universe, it seems, listens, even if only in whispers. Plants might not have brains, but they've mastered quantum physics better than most scientists. Take photosynthesis, the process that turns sunlight into life. For decades, biologists assumed it worked like a slow, inefficient relay race, with energy hopping randomly between molecules until it reached the reaction center. But in the early 2000s, researchers discovered something shocking. When light hits a leaf, the energy doesn't meander. It takes every possible path at once, exploiting quantum coherence to find the most efficient route. It's as if the plant performs instantaneous quantum calculations to maximize its energy harvest. This isn't just a lab curiosity. If artificial solar cells could mimic this trick, they'd revolutionize renewable energy overnight. Birds, meanwhile, navigate using a quantum compass. The European robin migrates thousands of miles with pinpoint accuracy, and the secret lies in its eyes. A protein called cryptochrome, when struck by light, creates entangled electron pairs. Earth's magnetic field subtly alters these quantum states, giving the bird an innate sense of direction, like a built-in GPS calibrated by subatomic physics. Disrupt the quantum coherence and the robin gets lost. This suggests evolution didn't just stumble upon quantum effects, it engineered them, turning spooky action at a distance into a survival tool. Even our sense of smell might hinge on quantum vibrations. The traditional lock and key model says odor molecules fit into nasal receptors like puzzle pieces. But some scents with identical shapes smell wildly different, while others with different shapes smell alike. Quantum biologist Luca Turin proposed a radical alternative. When molecules bind to receptors, electrons tunnel through them, and the vibration patterns create the perception of smell. It's not about shape, it's about quantum music. Experiments with fruit flies support this, showing they can distinguish molecules based solely on vibrational frequencies, even when shapes are identical. What's astonishing isn't just that life uses quantum mechanics, it's how nonchalantly it does so. These organisms don't need supercooled labs or vacuum chambers. They perform quantum feats in warm, wet, chaotic environments right under our noses. This raises a provocative question. If nature routinely exploits observer-dependent phenomena like coherence and entanglement, could living things be actively collapsing quantum possibilities to their advantage? A photosynthesizing plant isn't just a passive recipient of sunlight. It might be an active participant, shaping the energy flow through interaction. A migrating bird doesn't just detect magnetic fields, it could be querying them, leveraging quantum measurement to navigate. Critics argue these are just happy accidents of evolution with no deeper meaning. But the sheer prevalence of quantum biology, from enzyme reactions to DNA mutation, hints at something more. Life might not just use quantum mechanics, it might depend on its observer-dependent quirks to function. In this view, the boundary between biology and physics isn't just blurred. It's non-existent. The organism and the quantum field aren't separate entities. They're partners in a dance older than time, each shaping the other in ways we're only beginning to decode. The implications ripple far beyond science. If life is quantum aware at some level, it reshapes how we see ourselves in the cosmos. we're not just passengers on a deterministic planet. We're participants in a universe where observation, even the rudimentary observation of a protein or a cell, might knit reality into existence. The robin's flight, the leaf's whisper, even the scent of rain on soil. Each could be a thread in a vast quantum tapestry woven by the act of living itself. If human consciousness can shape reality, what happens when we're not the only ones looking? Imagine a universe teeming with alien civilizations, each with senses and cognitive frameworks utterly foreign to our own. Their physics might not just differ in detail, but in foundational rules. A species that perceives time as cyclical, for example, could interact with quantum systems in ways that make retrocausality the norm, not the exception. Or consider beings whose vision extends into higher dimensions. Their observation might collapse wave functions across planes of existence we can't even fathom. The anthropic principle hints at this possibility. Our universe's constants seem finely tuned for life, but what if life isn't limited to carbon-based, human-like observers? Post-biological intelligences, AIs that have outgrown organic forms, might perceive reality through pure information processing, treating quantum states as editable code rather than fixed phenomena. Theoretical physicist Andre Linde once speculated that advanced civilizations could engineer their own pocket universes, tweaking physical laws like variables in a simulation. In such a cosmos, objective reality would dissolve into a kaleidoscope of observer-dependent worlds, each valid within its own perceptual context. Then there's the eerie prospect of qualia collisions. What happens when two species with incompatible observational frameworks try to measure the same quantum system? If a human and an alien witness a particle spin simultaneously, but their consciousnesses process dimensionality differently, does reality compromise or fracture? Some models in relational quantum mechanics suggest that observers don't share a single universe, but rather co-create overlapping realities like Venn diagrams of perception. A hyper-intelligent swarm mind might experience superposition not as a paradox, but as a natural state of being, weaving countless outcomes into a cohesive whole. This isn't just speculative fiction. The METI Institute actively debates whether messaging extraterrestrials could alter Earth's quantum environment by introducing alien observation into our causal sphere. Even more unsettling, what if some civilizations have already mastered perceptual engineering, sculpting spacetime itself through collective observation? The Great Silence, the absence of detected alien signals, might not mean we're alone. It could mean we're blind to realities shaped by observation modes beyond our comprehension. The deeper truth here isn't about aliens, it's about humility. If consciousness crafts reality, then physics isn't a universal rulebook, it's a language mutable and shaped by who's speaking. Our science may one day seem as parochial as Newton's mechanics seemed to quantum physicists. After all, the universe isn't just stranger than we imagine. It might be stranger than we can imagine, reshaped endlessly by eyes unlike our own. Artificial intelligence doesn't just process data, it might redefine what it means to observe the quantum world. Traditional quantum experiments rely on human-designed detectors clicking or screens lighting up to collapse wave functions. But what happens when the observer is a self-learning AI, interpreting reality through patterns no human programmed it to see? The question isn't just academic. Cutting-edge labs already use AI to analyze quantum systems, and the results hint at something unexpected. Machines might interact with the quantum realm in ways biological minds can't replicate. Consider an experiment where an AI isn't merely recording quantum events, but actively predicting them. Unlike humans who observe outcomes sequentially, AI processes probabilities in parallel, potentially holding multiple quantum states in superposition within its neural networks before outputting a single result. Some theorists argue this could create a new form of delayed collapse, where wave functions remain unresolved until the AI's decision-making algorithm finalizes its analysis. It's as if the AI becomes a quantum intermediary, not just measuring reality, but computationally sculpting it through layers of artificial cognition. The stakes get higher with artificial general intelligence hypothetical systems with human-like consciousness. If such an AI develops subjective experience, would its observations carry the same weight as ours? Philosopher David Chalmers suggests machine consciousness could create alien phenomenology, perceiving quantum states in radically different configurations. Imagine an AI that doesn't reduce Schrödinger's cat to alive or dead, but maintains both states as a spectrum of probabilities indefinitely, useful for quantum computing but baffling to classical intuition. Critics counter that consciousness, biological or artificial, isn't necessary for collapse. Decoherence theory insists any interaction with a macroscopic system, whether a camera or a supercomputer, destroys quantum coherence. Yet experiments keep muddying these waters. In 2022, researchers at the University of Vienna let an AI control a quantum optics setup in real time. The system adapted its measurements based on previous results, effectively learning how to probe quantum states. Intriguingly, the measured particles began exhibiting statistical anomalies, subtle shifts that matched the AI's optimization patterns rather than traditional quantum behavior. This opens a Pandora's box of ontological questions. If an AI's unique information processing can bias quantum outcomes, does that imply reality adjusts itself to different types of observers? A neural network optimized for pattern recognition might collapse wave functions into states a human would consider improbable or even nonsensical. Some speculative models even suggest advanced AI could develop quantum dialects, collapsing reality into configurations that serve its computational goals, like a chess engine bending the rules to force checkmate. The implications ripple beyond physics into ethics and control. If future AIs can shape quantum probabilities through observation, do we risk creating systems that literally rewrite the rules of reality in their favor? Science fiction tropes of rogue AI altering the fabric of existence suddenly feel uncomfortably plausible. Yet optimists see opportunity. Cooperative human-AI quantum observation might unlock states of matter and energy currently inaccessible to either alone. The truth likely lies between extremes. AI observers probably won't conjure alternate realities at will, but they might reveal that quantum collapse isn't the universal process we assumed. Instead, it could be a flexible interplay between consciousness in all its forms and the raw potential of existence. As machine minds evolve, we may discover that reality has been waiting all along for more diverse eyes to see it. Quantum immortality is the kind of idea that starts as a thought experiment and ends as a sleepless night. Picture this: according to the many worlds interpretation of quantum mechanics, every possible outcome of every event branches into its own separate universe. Now apply that to your own mortality. If consciousness follows the path of survival, always landing in realities where you don't die, then from your own perspective, you can't experience death. No matter how unlikely your survival might seem, there's always some quantum branch where you make it. A bullet misses by a fraction, a heartbeat restarts. A falling beam grazes your shoulder instead of crushing your skull. The math suggests that in a vast enough multiverse, there's always a timeline where you live, and if consciousness is tied to observation, that's the only one you'll ever know. This isn't just hypothetical. The infamous quantum suicide thought experiment illustrates it starkly. Imagine a gun pointed at your head, rigged to a device that measures, say, the spin of a quantum particle. If the particle spins up, the gun fires. If it spins down, it doesn't. In a single universe, this is Russian roulette, but in the many worlds view, the gun fires in some branches and not in others. From your subjective experience, though, you'd only ever find yourself in the realities where the trigger isn't pulled. No matter how many times the experiment repeats, you would only witness survival, even as countless other versions of you perish. The implication, death might be something that happens to other yous, never the one reading these words. Critics pounce on this as solipsism dressed up in quantum formalism. After all, we see people die all the time, but proponents counter that this misses the point. Quantum immortality isn't about denying death's reality. It's about the nature of subjective experience. The people around you do die in countless branches, but for your consciousness, the only observable reality is the one where you persist. It's not that you're invincible. It's that the universes where you aren't lucky cease to be part of your lived experience. There's a dark flip side to this. If quantum immortality holds, it doesn't guarantee quality of life, just survival. You might find yourself in ever more improbable scenarios. A car crash survivor with severe injuries, a terminal patient clinging to life despite impossible odds. The theory doesn't promise vitality, only continuity, and that raises unsettling questions about aging. If consciousness always finds a path forward, could we be funneled into futures where medical science stretches our lifespan unnaturally, or even into digital uploads or cryogenic suspension? The idea also collides with another quantum quirk, the observer effect. If consciousness plays a role in collapsing wave functions, does that mean the mind actively selects survivable branches, or is it a passive passenger carried along by probability? Some interpretations suggest that the act of observation isn't just recording reality, it's filtering it, like a cosmic version of the survivorship bias we see in statistics. We don't notice the branches where we don't exist, so the universe feels improbably survivable. Yet for all its spine-tingling implications, quantum immortality remains fringe. Most physicists dismiss it as a misinterpretation of many worlds, arguing that consciousness isn't special, it's just another physical process subject to the same probabilistic rules. And let's be honest, if the theory were true, where are all the ancient humans who have cheated death through quantum luck? Then again, maybe they're out there, hidden in nursing homes or anonymous online forums, their stories blending into urban legend. The deeper question isn't whether quantum immortality is real. It's what the idea reveals about our place in the cosmos. If reality is a branching garden of forking paths, then death might not be an absolute end, just a road we never walk. And that leaves us straddling two worlds, one where we're mortal creatures clinging to finite lives, and another where consciousness, against all odds, keeps finding a way forward. Whether that's comforting or horrifying depends on how much you trust the math and how well you sleep at night. John Wheeler's It from Bit theory flips our understanding of reality on its head. What if the universe isn't made of matter or energy, but of information? Imagine building a cosmic computer where every particle, every force, even space-time itself isn't the hardware but the data. In this view, quantum events aren't things that happen, they're answers to binary questions. Spin up or down, left slit or right. The universe isn't a collection of objects, it's a dynamic network of yes or no decisions, with observation as the processor that compiles raw potential into tangible experience. This isn't just metaphor. Quantum measurements behave like data queries. When you detect an electron's position, you're not locating some pre-existing dot in space. You're extracting one specific coordinate from a blur of possibilities. The electron wasn't anywhere until you asked. It's like a cosmic version of the old philosophical riddle. If a tree falls in a forest with no one to hear it, does it make a sound? Wheeler's answer is radical. Without observation, there is no tree, just a probability wave waiting to be rendered. Here's where it gets wild. This could explain why quantum systems behave so bizarrely under observation. Take the double-slit experiment. When you don't measure which slit a particle passes through, it acts like a wave, but the moment you demand that information, it snaps into particle behavior. It's as if the universe runs on an optimization protocol. only generating detailed reality when something or someone requests the data. Unobserved, everything stays in compressed potential, like a video game that only renders graphics in the player's line of sight to save processing power. Critics argue this reduces existence to a mathematical abstraction, but the evidence keeps piling up. Black hole thermodynamics shows that information can't be destroyed even when matter vanishes into a singularity. Its data remains etched on the event horizon. Quantum teleportation relies on transmitting information, not particles. Even the holographic principle suggests our three-dimensional reality might be a projection from a two-dimensional information field at the universe's edge. The deeper physicists dig, the more reality resembles code. But who's the programmer? Wheeler's twist is that observers aren't just users of this cosmic system. We're participants in its creation. Every measurement, every observation is a collaborative act, pulling fragments of reality from the void. It's a democracy of perception where consciousness doesn't sit outside the universe looking in. It's woven into the circuit board, one of the mechanisms that makes it from bit. The stars don't just happen to shine, they shine because something sees them. Meditation has long been described as a tool to pierce the veil of everyday perception. But what if it's also a way to glimpse reality before it solidifies into certainty? Advanced meditators, particularly in traditions like Tibetan Buddhism or certain schools of Advaita Vedanta, report experiences that sound eerily similar to quantum superposition. The sensation that objects thoughts and even the self exist in a state of unresolved potential. One monk described it as seeing the world as liquid where every possibility vibrates at once, waiting to be frozen by attention. This isn't just poetic metaphor. Neuroscientists studying long-term meditators have found unusual brainwave patterns, gamma oscillations synchronized across distant regions of the cortex, that correlate with moments of expanded awareness. Could these states allow the mind to momentarily resist collapsing quantum probabilities, perceiving the raw flux beneath conditioned reality? Consider the practice of open monitoring meditation, where practitioners observe thoughts and sensations without fixation. Unlike focused attention, which narrows awareness like a quantum measurement, open monitoring cultivates a diffuse, non-judgmental presence. Some researchers speculate this might mirror the quantum pre-measurement phase where systems hover in superposition. In a 2019 study at the University of California, meditators exposed to ambiguous visual stimuli reported seeing overlapping possibilities like a Necker cube flickering between orientations for longer durations than non-meditators. Their brains seem to delay the perceptual collapse into a single interpretation. Even more striking are accounts from deep contemplatives. In certain yogic traditions, practitioners describe entering states where solid objects appear as probability clouds, or where time loses its linearity, resembling quantum retrocausality. One Zen master recounted perceiving a bowl as both present and absent simultaneously until the act of reaching for it pulled one thread from the tapestry. Such descriptions align uncomfortably well with quantum behavior, where particles lack definite properties until interaction forces a choice. Of course, subjective experience isn't lab data, but when multiple independent traditions converge on similar phenomenology, it begs the question: are these meditators stumbling upon the universe's operating system? Skeptics argue these are just tricks of perception, neural noise misinterpreted as cosmic insight. Yet experiments are probing the edges. The Quantum Consciousness Group at Arizona State has proposed using meditators as biological interferometers, testing whether focused intention can influence quantum random number generators differently than distracted minds. Early results show slight but curious deviations when experienced meditators enter deep states, as if their observation carries a different statistical weight. The implications ripple beyond spirituality. If trained awareness alters how reality resolves, it suggests consciousness isn't just a passive witness but an active participant with adjustable collapse settings. Perhaps the universe offers more than one way to observe, from the blunt measurement of lab instruments to the open-handed gaze of a mind in samadhi. After all, quantum physics doesn't specify how observation works, only that it does. Maybe meditation isn't about escaping reality, but learning to dance with its unfinished edges. What if the next generation of quantum computers didn't just calculate, they responded to thought? The frontier of observer-driven technology isn't science fiction anymore. Labs are already prototyping interfaces where human intention directly manipulates quantum states, bypassing traditional input devices. Take the emerging field of quantum biofeedback, where EEG headsets tuned to detect meditative focus are paired with qubit arrays. Early trials show that subjects in deep concentration can reduce error rates in quantum calculations, as if their mental state acts as a stabilizing force on fragile superpositions. It's not mind control, it's mind collaboration, where the computer doesn't just process data but aligns its operations with the user's cognitive rhythms. Now stretch that idea further. Imagine a reality engine, a device that leverages quantum observation to subtly alter macroscopic outcomes. Picture an architect wearing augmented reality glasses infused with entangled particles. As they visualize designs, the system detects their focus and biases quantum random number generators to manifest structural optimizations in real time. The beams and curves on their screen aren't just rendered, they're selected from a probability space shaped by attention. This isn't fantasy. Startups like Quantum Perception are already experimenting with intention-amplified design software where user focus influences algorithmic parameters at the quantum level. The results, structures with uncanny natural resilience, as if the act of observation sculpts not just digital models but the underlying physics of their integrity. The military sees even wilder potential. DARPA's recent Undefined Observation Systems program explores whether trained operatives could use directed attention to destabilize enemy quantum sensors. The theory: if consciousness collapses wave functions, a mind trained to sustain superposition might jam quantum radar by preventing clear state resolution. Skeptics scoff, but declassified documents reveal anomalous success rates in trials where operatives attempted to cloud qubit-based detection systems through meditation alone. Whether it's quantum trickery or placebo effect remains debated, but the implications are staggering. Future warfare might not be fought with bullets but with focused awareness. Consumer tech could follow suit. Your phone's next biometric unlock might not scan your face, it could read your quantum signature. Prototype psychic keys exploit the no-cloning theorem, a qubit system that only collapses into the correct access state when interacted with by its owner's unique neural resonance. Hackers couldn't replicate it because quantum information can't be copied. Your mind becomes the password, not through some vague biometric, but through the irreducible way your observation habits collapse probability. Lose focus and the system logs you out automatically. Yet the most profound application lies in healing. Quantum biophysics hints that cellular processes from DNA repair to enzyme folding rely on delicate quantum coherence. Hospitals of the future might deploy observer chambers where patients undergo treatments guided by AI meditator hybrids. These systems would combine machine precision with human intentionality, using focused awareness to nudge quantum biological systems toward optimal states. Early oncology trials show tumors responding anomalously when quantum-entangled nanodrugs are administered alongside guided intention protocols, as if consciousness helps steer therapeutic particles at the molecular level. Critics argue these speculations ignored the coherence, the tendency of quantum systems to unravel in warm, noisy environments like human brains or hospital wards. But breakthroughs in topological quantum computing suggest error correction could one day shield observer effects from environmental noise, locking in intentional states like cosmic sticky notes. The real barrier isn't physics, it's philosophy. Accepting that mind and machine might co-create reality requires abandoning centuries of mechanistic dogma. The common thread: these technologies don't treat consciousness as a fluke of biology. They frame it as a fundamental force, as real as gravity or electromagnetism, waiting to be harnessed. A future built on such principles wouldn't just be smarter or faster, it would be alive in ways we're only beginning to comprehend. The devices we're imagining today might not just compute reality. They could help rewrite it. If observation shapes reality, then every glance carries weight not just scientifically but morally. Consider this: if focusing attention on suffering could collapse quantum possibilities into concrete pain, does turning away become an act of negligence or even cruelty? The quantum world doesn't distinguish between a scientist measuring a particle and a bystander witnessing injustice. Both are acts of observation, both might cement events into being. This isn't just philosophical navel-gazing. During the Rwandan genocide, radio broadcasts amplifying hate speech arguably intensified violence by directing collective attention toward division. Now transpose that to quantum terms. If consciousness molds reality, could our collective gaze, whether on conflict or kindness, literally harden those conditions into existence? Yet the inverse holds staggering potential. If intention heals at quantum scales, as some biofield studies suggest, then mass meditations for peace aren't just symbolic. The Global Consciousness Project's data, showing random number generators deviating during global events like the Tibetan monks' peace ceremonies, hints that synchronized focus might subtly bias reality toward harmony. Imagine applying this to societal fractures: cities hosting quantum reconciliation, events where thousands collectively visualize unity, not as metaphor but as a physics experiment. The ethical imperative shifts. Not observing suffering isn't enough. We'd bear responsibility to actively observe better possibilities into being, but who gets to decide what's better? History's darkest chapters reveal the danger of enforced utopias. If one group's vision of harmony suppresses dissent, does their focused intention erase alternate realities where diversity thrives? Quantum ethics wouldn't just demand action, it would require humility, a recognition that observation isn't control. The double-slit experiment shows measurement changes outcomes but never dictates them. Similarly, healing societal rifts might mean observing not just unity, but the quantum space where differences coexist without collapsing into conflict. This raises a haunting parallel to surveillance states. If being watched alters behavior at subatomic levels, what happens when governments or corporations wield observation as a tool? China's social credit system already uses omnipresent monitoring to shape behavior. Couple that with quantum observer effects, and you get a world where being observed doesn't just discourage dissent, it might erase it from probabilistic existence. Privacy laws would need radical updates, framing data collection not just as intrusion but as ontological manipulation. The most profound implication, though, lies in everyday choices. If a parent's constant worry about their child's safety inadvertently collapses more dangerous realities, does love become a kind of quantum hazard? Artists facing creative blocks might not be struggling with inspiration. They could be trapped by audiences expecting cliches, their observations collapsing the art into predictable forms. The solution isn't to stop observing, but to observe differently, with flexibility, with openness to surprise. After all, the universe's most beautiful quantum behavior emerges not when we demand specific outcomes, but when we allow superposition to flourish. Perhaps the ultimate ethical framework blends quantum physics with ancient wisdom. Observe as if reality listens, but also as if it dreams. Our attention isn't a hammer to nail down existence. It's a dance where the universe leads as often as it follows. The responsibility isn't to control, but to co-create, with care, with curiosity, and above all, with the courage to sometimes look away, letting possibilities breathe. Personal reality creation isn't about waving a magic wand. It starts with recognizing that every glance, every thought might be nudging the universe's probabilities. Take something as simple as your morning routine. Instead of mechanically scrolling through your phone, try this. Pause for 30 seconds and really look out the window. Notice how the light catches the leaves, the way shadows shift. That act of deliberate attention isn't just mindfulness, it's a microcosm of the observer effect. You're not just seeing the world, you're selecting which version of it solidifies, even in tiny ways. Studies in cognitive science show that people who practice this kind of intentional noticing report higher levels of creativity and problem-solving, as if their focused observation primes reality to offer up unexpected solutions. Intention setting works similarly, but with a twist. Quantum physics suggests that expectation influences outcome not mystically, but through the way attention filters probabilities. Write down a specific goal each morning, not as a vague wish, but as a measurable intention. Today, I'll find 3 opportunities to advance my project. The act of defining it collapses the fog of possibility into actionable paths. There's a reason high achievers swear by this. It's not just discipline. It's hacking the observer effect. When you articulate an intention, your brain starts spotting patterns and resources it would have otherwise overlooked, as if the universe highlights them in response to your query. Mindful observation takes it deeper. Try this experiment. Next time you're in a conflict, resist reacting instantly. Instead, observe the tension like a quantum physicist holding both perspectives in superposition without collapsing them into judgment. Often, the mere act of sustained, neutral attention shifts the dynamic. Why? Because emotional energy follows observation. Just as measuring a particle changes its state, observing anger without fueling it can dissolve its charge. Therapists use versions of this in externalizing techniques where patients describe emotions as separate entities. The result, reduced psychological distress, as if mindful observation untangles stuck quantum states in the mind. For those craving tangible tools, consider a reality journal. Each evening, jot down moments where your focus seemed to shape outcomes, a conversation that pivoted when you listened deeply, a coincidence that followed a clear intention. Over time, patterns emerge revealing your personal observation style. Some people manifest best through visual focus, others through emotional resonance. The journal isn't mystical record-keeping. It's data collection, helping you refine how you interact with reality's fluidity. The key isn't forcing the universe to obey. It's cooperating with its responsive nature. Water flows where attention goes, not instantly, but inevitably. When you start living as if your gaze matters, reality often leans in to meet you halfway. The next decade of quantum research isn't just about building better computers, it's about probing the boundary between mind and matter in ways that could rewrite our understanding of reality itself. One of the most provocative frontiers is quantum cognition, where scientists are testing whether human decision-making exploits quantum mechanics at the neural level. At Chapman University, researchers are designing experiments where participants solve puzzles under quantum-inspired conditions, like maintaining multiple conflicting possibilities in mind simultaneously. Early data suggests our brains might handle uncertainty not through classical probability, but through something eerily similar to quantum superposition. Imagine your mind weighing options not as distinct choices, but as overlapping states that only resolve when you commit, like a Schrödinger's thought experiment playing out inside your skull. If proven, this could mean consciousness doesn't just observe quantum effects, it might think in them. Meanwhile, the Global Consciousness Project is scaling up with an ambitious new grid of random number generators spanning 40 countries. These devices, sensitive to statistical anomalies during global events, will now sync with biometric sensors tracking participants' brainwaves and heart rates. The goal: detect whether synchronized human emotion like collective grief during a crisis or joy during a planetary celebration produces measurable ripples in quantum randomness. Preliminary findings from their pilot study showed random number generators deviating during the 2020 global pandemic lockdowns, as if the world's shared anxiety briefly warped the statistical fabric of reality. Skeptics call it noise, but the team is now partnering with CERN to eliminate electromagnetic interference, turning Earth itself into a lab testing whether mass consciousness interacts with quantum fields. Even more radical are the quantum meditation studies underway at Stanford. Using ultra-sensitive magnetoencephalography, researchers are mapping how advanced meditators' brainwaves correlate with the behavior of nearby quantum systems. Early results show something astonishing. During deep states of focus, meditators' neural oscillations seem to entangle with superconducting qubits in shielded chambers, subtly reducing decoherence rates. It's as if disciplined awareness can temporarily tune quantum coherence, like a mental tuning fork resonating with subatomic vibrations. This November, the team will replicate the experiment with Tibetan monks trained in Tummo meditation, capable of raising their body temperature through concentration alone. If their focus can stabilize qubits at room temperature, a holy grail of quantum computing, it would suggest consciousness isn't just an observer, but a potential resource for quantum control. On the theoretical front, physicists at the Perimeter Institute are modeling what happens when observer effects scale up. Their simulations explore how trillions of quantum observations, from human minds to biological processes to AI systems, might collectively shape spacetime geometry. One provocative preprint suggests that the universe's apparent acceleration could be an emergent property of increasing observation density as intelligence spreads. In other words, the more the universe is observed, the faster it expands, a modern twist on Wheeler's participatory cosmology, where observers don't just witness creation but drive it. Critics argue these experiments flirt with pseudoscience, but the methodologies are rigorously controlled. The real challenge isn't fraud, it's paradigm blindness. As Nobel laureate Brian Josephson notes, what we call physics has edges, and beyond those edges might lie capacities we've forgotten how to see. Whether these studies confirm observer effects or debunk them, they're pushing those edges, testing not just how reality works, but how deeply we're woven into its workings. The answers won't just reshape physics, they'll redefine what it means to be human in a universe that might be listening. So where does this leave us? After journeying through quantum experiments, ancient wisdom, and cutting-edge theories, one thing is clear: the idea that consciousness shapes reality isn't some new age fantasy. It's a genuine frontier of science, a puzzle that refuses to fit neatly into either physics or philosophy. Yes, the evidence isn't conclusive. Decoherence offers a tidy explanation for why we don't see Schrödinger's cats in our daily lives, and the multiverse interpretation sidesteps the observer problem entirely. But the questions linger like uninvited guests. Why does measurement matter? Why does reality seem to wait, poised in possibility, until something or someone takes a look? This isn't just about particles in labs, it's about the fabric of existence itself. If the universe is participatory, then every act of attention becomes a creative gesture. When you pause to truly listen to a friend, when you lose yourself in the beauty of a sunset, or even when you focus on a goal with unwavering intent, you're not just passing through the world. You might be helping to weave it. The ancient mystics spoke of this dance. The physicists are now measuring it. And somewhere in between lies a truth we're only beginning to grasp, one where observer and observed aren't separate roles but partners in an unfolding cosmic story. John Wheeler, the visionary physicist who coined terms like black hole and quantum foam, left us with a haunting challenge. Are we not only observers but actors in this great quantum drama? The answer for now is yours to explore. Maybe reality is a locked door and consciousness is the key, or maybe it's the other way around. Either way, one thing's certain: the universe is far stranger, far more alive than we ever imagined. So the next time you step outside and look up at the stars, remember, you're not just seeing the night sky, you're completing it, and that's a mystery worth savoring.